Hello and welcome back to AP Psychology. My name is Mrs. Seguin and today we're going to be covering your sense of hearing. This is part 4 of Unit 3, so we are over halfway there. We're getting there, guys. Alright, let's go ahead and get started. Our learning target for the day, we're going to describe the hearing process, including the specific nature of energy transduction, relevant anatomical structures like, the ear, and specialized pathways in the brain for each of the senses. Okay, the first thing you need to know about hearing is the frequency or the pitch. So the frequency is the dimension of the frequency is determined by the wavelength of the sound. So remember when we talked about the eye, the wavelength of the sound was it's peak to peak, right? We're measuring from peak to peak. So a longer, slower wave registers as red for the eye, and a shorter, tighter wave registers as blue or purple for the eye, right? In your ears, a longer wave means a lower sound, a lower pitch, right? A tighter wave or a shorter wavelength means a higher sound. Humans can hear sounds at frequencies from about what we call hertz. That's how we measure sound frequency, right? From about 20 hertz to 20,000 hertz. So we've got some range in there. The hearing that we experience is best around 3 to 4,000. And this is where human speech tends to be, because otherwise voices would be entirely too high or too low and irritating, right? Okay, so the higher the frequency of the sound, the higher the pitch of the sound. So the higher the frequency of the wave, the higher the pitch of the sound. And remember, a higher frequency means a shorter wavelength. Okay, the intensity of the sound is its loudness. So a sound is intense when it's loud, right? This is the amount of energy in a wave determined by the amplitude. So it's related to perceived loudness. If you've ever done a voice recording of yourself, you have an app for that on your phone. If you've ever done a voice recording, I want you to start out, and I want you to just try this real quick. I want you to start out where you just whisper into it, like really close to your face, and keep it right next to your mouth, right? I want you to whisper into it, and then I want you to yell, and I want you to watch what the wavelength or what the amplitude or the height of that wave achieves. So loudness is measured in units called decibels. Decibels are units of sound, right? Above a certain point, the decibels can be actually damaging to the ear. So we need to be careful with our hearing to not be in loud situations. And by that I mean it can be pretty loud, in really loud situations frequently. Okay, the ear looks just about as complicated as the eye, right? So there's 3 major sections of the ear. We have the outer ear, the middle ear, and the inner ear. Okay, so the outer ear captures those sound waves and it funnels them down your ear canal, right? Your auditory canal, to the eardrum, which sits at the back of your auditory canal. It stimulates the eardrum, and it's more complicated than this, but I am trying to simplify it. Stimulates the eardrum, and then the sound waves trigger a response in the middle ear. The middle ear has 3 teeny tiny little bones. As a matter of fact, I believe they're the smallest bones in the human body. We call them the hammer, the anvil, and the stirrup. And now they have Latin names, but that's not what we're using today. So the hammer, the anvil, and the stirrup. And those trigger, there's a fluid-filled organ in your inner ear called the cochlea. The cochlea not only controls the stimulation of the auditory nerve, but also your balance. So if you've ever had vertigo, it's probably because your ears are all messed up or they're clogged, and so your brain is trying to achieve balance, but it doesn't have full use of the ear. Okay, so the cochlea, a little bit more on this, is a coiled, bony, fluid-filled tube in the inner ear. It looks like a little seashell, okay, that transduces sound vibrations to auditory signals. In other words, it takes those sound vibrations, it runs them through the fluid, and it turns them into an electrical signal that it sends up the auditory nerve to the brain, where it interprets the sound. So there's a very complex process with you hearing my voice right now and actually doing something with what I'm saying. Okay, theories of hearing. Frequency theory states that the rate of nerve impulses traveling up the auditory nerve matches the frequency of a tone, therefore enabling us to sense its pitch. So have you ever heard of someone being tone deaf? This is probably, they may or may not actually be tone deaf scientifically. Basically what this means is they struggle to figure out what the pitch is of a musical note, and so they'll sing and it's totally off the note because they can't detect what that is. So that the rate of the nerve impulses, so how quickly the brain is getting signals up that auditory nerve, matches the frequency of the tone. Remember, the frequency, how many times the wave passes, right? Thus enabling you to sense its pitch. And I know it's complicated. Place theory suggests that sound frequencies stimulate the basilar membrane at specific places, resulting in perceived pitch. The localization of sound. Because we have two ears, sounds that reach one ear faster than the other make us localize the sound. So for example, if someone said your name and they were standing like behind you but off to, let's say, your left, this ear, you're going to hear with your left ear before you hear with your right ear. And so you're not automatically going to turn to your left, perceiving that the person is behind you to your left, right? Your brain knows where to go based on which ear hears it first. Okay, hearing loss. This happens in a lot of people, right? Just as when you drive a new car off the lot and it depreciates in value due to your use of the car, your ear's hearing ability decreases as you use it, unfortunately. This is why older people who have been using their ears for 60, 70, 80 years tend to start having hearing loss issues. So noise-induced hearing loss is basically exactly what it sounds like. The noise over time ends up damaging the ears just slightly, and as that damage builds up, you end up hearing less and less and less and less and less. So this is the progressive inability to detect higher frequency sounds due to damage to the hair cells accrued over time and with use. So as you use your ears and they become old and damaged, they struggle to hear higher sounds. Generally, any sound loud enough to produce ringing in the ears can cause damage. That's also known as tinnitus, by the way, ringing in the ears. High-intensity sounds can actually rip off the hair cells. Now, they're not really hairs, but they're very, very fragile cells that collect the sound waves as they're going through your ear. And they're located in the inner ear. They're very, very delicate. And really loud sounds can destroy them in your inner ear. Conduction deafness. So this is hearing loss caused by damage to the mechanical system that conducts sound waves to the cochlea. This can be corrected with surgery or with hearing aids. So basically, as the waves are being transferred through the parts of the ear eventually to the cochlea and then toward the auditory canal, there is a point where or there is damage to that system that makes it to where it's less efficient in conducting the sound waves. And then we get sensory neural deafness. This is hearing loss caused by damage to the cochlea's receptor cells or to the auditory nerve, also called nerve deafness. This is permanent. So this is the cochlea is damaged, therefore it cannot process the sound waves, or the auditory nerve itself is damaged, therefore even if the rest of the ear worked perfectly, the signal is never going to get to the brain, therefore you're never going to register the signal. Okay, one way that we can solve hearing loss is what's called a cochlear implant. So this is a small electronic device, it's very complex, that can help to provide a sense of sound to a person who is very, very deaf or severely hard of hearing. An implant doesn't restore normal hearing, but it can give a deaf person a useful representation of sounds in the environment and help him or her to understand speech. So it just makes it easier to function without the sense of hearing. A quick Google search, and I encourage you to do this because the videos are heartwarming. Google babies who get their first sets of hearing aids and they hear their mother's voice for the first time. It is absolutely the most precious videos. All right, that is all I have for you today. I will see you in class tomorrow. Bye.